Welcome. This is the CVPR 2021 presentation on our paper, How Well Do Self-Supervised Models Transfer? This work was completed by myself, Linus Eriksson, Henry Gauck, and Timothy M. Hospitalis. I'll start by describing a standard supervised pipeline. Given a dataset of images, human annotators often spend thousands of hours manually creating labels which a model then can be trained to predict. This pipeline limits the number of images that can be used in training, as the annotation process is slow and expensive. Self-supervised learning attempts to solve these problems by instead automatically generating pseudo-labels from the structure of the data. This can allow using more images for training, while still maintaining the powerful discriminative framework of supervised learning. After training, the representations can be transferred to new tasks and domains, thereby reducing the need for large amounts of labeled data in downstream training. In the past couple of years, self-supervised methods have improved significantly and now approach supervised performance on the standard ImageNet benchmark when using identical architecture. Despite still being behind on ImageNet, there has been initial evidence that self-supervised models transfer better to new tasks. In this work, we study this transfer performance of self-supervised pre-trained models, trying to answer the following questions. How does self-supervised transfer compare to supervised transfer? Is there a best self-supervised method overall? Has the community overfit to ImageNet as a benchmark? And do self-supervised and supervised features represent the same information? To answer these questions, we obtained 13 pre-trained self-supervised models, along with a supervised baseline. All models use the same ResNet 50 architecture and were pre-trained on ImageNet by the original authors without using any labels apart from the supervised model. Differences in models stem from their training objectives and hyperparameter details like epochs, batch size, and data augmentation. Our transfer evaluation covers a wide range of tasks, including many-shot and few-shot recognition, object detection, surface normal estimation, and semantic segmentation. The datasets we use exhibit a wide range of similarity to the source ImageNet data, from the very similar CIFAR-10 to the very different medical X-ray images. Now we present our results. On the x-axis, we plot the ImageNet accuracy of the pre-trained model, and on the y-axis, the average logit transformed transfer performance. In addition to covering different tasks and datasets, we also look at both linear evaluation and fine-tuning in the many-shot setting, small domain shift and large domain shift in the few-shot setting, object detection from a frozen and fine-tuned backbone, and finally our two dense prediction tasks of surface normal estimation and semantic segmentation. With these results, we can answer some of our earlier questions. We first look at how the self-supervised models compare to the supervised baseline represented by the green star. Across all but one setting, self-supervised models outperform supervision, showing their superior transferability. But there is no single model that dominates all settings, showing the community still has a way to go to reach truly general features. To answer our third question, we look at the correlations in our results. We find that ImageNet performance is highly correlated with many-shot recognition in both the linear and fine-tuned settings. But the correlation is weaker and weaker as we look at few-shot recognition, object detection, and the two dense prediction tasks. This shows that in order to achieve more generalizable representations in the future, the community needs to consider wider benchmarks for evaluation. Next, we look at the properties of the features produced by the models. We find that the supervised baseline can better reconstruct images from its feature vectors, and part of the reason is that self-supervised models tend to lose color information, likely due to the heavy data augmentation used during training. The self-supervised models also have a wider attentive focus in contrast to the high spatial focus of the supervised baseline. Finally, we find that models trained through self-supervision tend to produce better calibrated classifiers for downstream recognition tasks. To conclude, in this paper we have conducted the first thorough and up-to-date empirical evaluation of state-of-the-art self-supervised transfer. We have found that the best self-supervised models usually transfer better than supervision, but the best model choice depends on the downstream task in question, as no model dominates overall. ImageNet performance is not reliably representative of non-recognition tasks or unstructured data, meaning that researchers should adopt a wider range of benchmarks to better impact the broader computer vision community. Finally, self-supervised features tend to discard color information, attend to wider regions of the image when making decisions, and have better uncertainty calibration for recognition tasks. Thank you for listening, and please find our full paper and codebase through these links.